Howdy, everybody. We're here for day 20 of Advent of Code. We're coming to the end. Again, thanks everyone for your comments and positive feedback. I'm getting good ideas of things to do next, getting great ways to improve. Like one thing I think I might do is after I'm done with the 25 days, my next video will kind of be talking about some of the input you guys have given and kind of looking into that in more detail, like how to improve the algorithms or how to understand them better. For example, yesterday's day, I think it was. We'll look at this graph in a second, but it turns out what I actually implemented was something akin to, it wasn't exactly a KD tree, but it was something along those lines. So it'd be fun to kind of talk about those and help understand them a little bit just so we know what's going on. But anyway, very thankful for all your input and stuff. And with that, let's go ahead and hop into day 20. So in this one, you fixed all the parts, and now they have a bunch of cables that connect all of the machines that the parts go to, and they're sending signals to try and or those. How do I describe it? Yeah, they have like cables that attach all the machines that are connected to these modules, and each of the modules do special things, but the idea is they send signals to each other, and eventually you end up with like all the modules receiving signals and doing highs and lows and stuff like that. We'll talk about it in detail a second, but your input essentially looks like this. And the idea is this is the module, and this is the symbol for the module. And then these are the destinations that it outputs to. So each module has some number of inputs and some number of outputs that you need to kind of track, right? So what do each of the modules look like? So if there's a percent sign, it's a flip-flop module. And the way what they say is you're just tracking the on or off position there. So it starts off, if it receives a high pulse, maybe I didn't describe that. The signals that are going through are high and low pulses. And so for the flip-flop module, if you receive a high pulse, you do nothing. If you receive a low pulse, you flip the state of the flip-flop module, and then you send a high pulse if it was off and a low pulse if it was on, right? So that's a little confusing, but you get the idea. Is you're ignoring high pulses. Whenever you get a low pulse, you're going to flip the switch and then send a correlating pulse to all of your destinations, right? So they have an example down here of these ones. You can see this has multiple destinations. These ones only have one. Some of them are more complicated, but the idea is whenever you receive a signal, you're going to send out you're going to do some logic and then send out some signals to your destination based on those logic, some or none, right? And so again, the flip flop is just maintaining a state of on or off, and whenever you receive a low signal, you're changing those states and sending out new signals. A conjunction is a little bit different. It has to remember all of the input signals that it's most recently received. And so you think if this one you think about, okay, so for the flip flop, I really don't care where I received it from. I'm just going to flip my own state. The conjunction, now you are kind of interested in the ones you received, right? Because you want to remember the most recent pulse you received from each of your connected inputs. So in this case, you're going to track some kind of list that says, okay, I have 3 inputs. They're all going to start at low. But when I receive a high from one, I need to say, oh, now I've received a high and it's now high. And then when you receive a low, you're going to switch those, right? From high to low. So what you do, again, what it says is you're going to track that state, and whenever you receive an input, you're going to update that input state. And then if all of them are high, you send a low pulse. Otherwise, you send a high pulse. So you can think of this conjunction as kind of I don't know. Again, it's tracking inputs, and it's like sending out high pulses until it's received a high from all of them. Um, uh, uh, in they've all, the last time that they all, how do I say this? The last time they were all, they all received an input, they were high, is the way to say it. Sorry if that's a confusing way to say it. That it did actually take me a little bit of time to think these through. It turns out the problems are not that hard, but as I was trying to grok what each of these do, it was a little bit like, okay, I think I understand. But if you read the paragraph a couple times, I think you'll get it. The idea is you're just tracking your inputs, and every time you receive an input, you're gonna flip it. You're gonna update the state of that input to either low or high based on what came in, and then you go check that, and if all of them are high, you send out a low. Otherwise, send out a high. Okay. The broadcast one, you only have one of these, but it is a simple one. And essentially, you just, whatever you receive from the input, you send out to all the destinations, right? So you broadcast them all. And then the last one is like there's a button that starts the process. And when you push the button, it sends a single low pulse to the broadcaster. So you can think of, they give you an example here, is like, here's an example input. You start at your broadcaster. When you push a button, the low signal goes here, and it broadcasts that low signal to A, B, and C. Then for A, you do the logic. For B, you do the logic. For C, you do the logic. And whatever those produce, you send those out to these, right? And it kind of describes this. Like if you push the button, here's what it looks like, right? So the general input is you push the button, you send a low to the broadcaster sends a low to A, the broadcaster sends a low to B, and the same thing to C, right? Notably, it says somewhere in here, pulses are always processed in the order they are sent. So if a pulse is sent to modules A, B, and C, then module A processes its pulse and sends more pulses. The pulses sent to modules B and C would have to be handled first, right? So the ones that A get processed, or the outputs of A shouldn't be processed until B and C have been processed from this part up here, is the way to think about it. And this is just the way to think about this, is when you see something like this, is they are sent in the, or they're processed in the order they're sent. That should signal to your mind a queue, right? So in Rust, I used a VecDeque where I'm pulling signals off the front and pushing signals on the back, right? So that allows me to do them in the order they're sent. That's just something to think about. But it gives you a thing, like a description of like, hey, here's what would happen if you pushed it once. And the idea is you're sending low and high signals to the different modules, and those modules are also producing low or high signals and sending them all over the place. Notably, some of the signals are terminal. So in this example they give you here, there's an output terminal, or sorry, an output module, but it's not defined anywhere. So you also will need to track that in code. Okay, so given all that, what is the question that part one is asking you? Basically, it's saying, okay, build all these modules, connect them together, run through the steps 1,000 times, right? They want you to push the button 1,000 times. Right here. To get the core cables warmed up, the elves have pushed the button 1,000 times. So they want you to basically go through this logic of pushing a button and handling the inputs, making sure you're handling them all in order, getting outputs from them, and putting those on the queue, and then doing that iteratively until you've gone through all of the inputs and outputs, right? You're gonna do that 1,000 times, and what it says is it wants you to track the lows and highs. And so the solution to the problem is push the button 1,000 times, track all the low and high signals that came out, including the one when you push the button. And so track all of those lows and highs, and then multiply them together to get your answer. So they say, hey, in the first example, if you when you push the button 1,000 times, it produces 8,000 lows and 4,000 highs. And you can kind of infer that from the first example, right? If you're looking here's the first example, and here's what it produces, right? You can see it does 1, 2, 3, 4, 5, 6, 7, 8 lows and 1, 2, 3, 4 highs. You might ask yourself, like, how do they stop? Oh, sorry. To continue on my point, there's 8 and 4. So if you do it 1,000 times, that's 8,000 and 4,000, and then you multiply them together to get whatever that is, 320,000, 3.2 million, 32 million. Did I do that? Yeah, 32 million. Apparently my maths are not on par today. I don't think I've ever I've talked about other trillions and quadrillions before. I probably haven't gotten any of those right. So but the idea is you track your lows and highs, multiply them together, and that gives you the thing. Okay, so you may be asking yourself, well, how does it stop? In the case of this first one, the reason, or sorry, this example right here, the reason this one stops is because this eventually sends a signal to A, but because it's a high signal, right? It ignores it, right? If a flip flop receives a high pulse, it ignores it and nothing happens. So that's why this one stops when the INV one sends a high message to A, it doesn't translate through. The same thing with this one down here. You are gonna get a lot of, like, there's like a loop in here. You can see A sends to INV, which sends to B, and B sends to con, but A sends to con as well, right? So you get these weird, you get, like, it's not a loop, I should say, but it's kind of like a tree. You get this weird tree. And but they all eventually make their way to output, and output is a terminal node which doesn't do anything with its inputs, right? It receives them. So eventually it ends, right? You still want to track the button pushes, what happens after you push the button, right? It's going to generate a low here, a low to A produces a high to INV and a high to con, and then INV produces a low, right? It's still, you're still tracing through it, but eventually you get con sends a high to output and con sends a low to output, and that kind of ends that little tree run, right? So that's something just to be clear. You get like a big graph in like this, but when you graph it out, you actually turn you can kind of see that there are like some cycles in it, but they all eventually kind of make their way down to some kind of terminal node, I guess is the way to think about it. Here is the graph, by the way. This is more interesting for part 2, and I realize it's an eye chart. Yours will look different. I think the inputs are different, but you should notice, you'll notice some things when we start talking about it in part 2. But here it is, right? And again, the way to think about this, or at least the way that I thought about it, is I'm just going to treat all of these modules as their own little unit, and they're going to receive some input, do some processing, and then produce some outputs for new destinations, right? For new modules. And you're just going to keep doing that until you run out. So how does that look in code? Well, first we want to have a pulse, right? So we want to know if the pulse is high or low, and we want some kind of communication to track that, right? And so the communication has the source, the destination, and the pulse you're sending. So, for example, a broadcaster, the source would be the broadcaster, the destination would be all of its destinations, right? And you do one for each of them, and then the pulse would be whatever you're sending, right? Because I wanted to treat this as a tree like this, right? I'm treating it and visualizing it as a tree of these destinations where each of the modules are nodes. An easy way to visualize this is to use a hash map, right? Where you say, like, oh, this module is named PD. So if the broadcaster says go to PD, I can always just look it up in the hash map. So the way that I did it, obviously you're having different parts, right? You're having these different modules. The way that I did that was use this handle communication trait. And if you're not familiar with Rust, traits are like interfaces in like Go or Java. The idea is any structure that has that implements this handle communication function for this trait can be used in a function that requires a trait that says, oh, I don't need to know like the concrete type. I just need to know that it handles this trait, right? So what does that look like in the code? Before I get into the details of each implementation, you can see here in my configuration, I just keep a map again of the name of the module and then a box line of handle communication, right? This is my way of saying I don't actually care what the underlying module concrete type is. I just want a pointer, that's what a box is, a pointer to something that implements that trait. And then I can do lookups and call handle communication. Because again, I'm not worried about the details of what it's tracking and what it's storing. I'm really just interested in um, what uh, what its handle communication function does, right? So if we go back here, I'm going to give it a communication for the handle communication. I'm going to give it this communication, right? Like where it came from. The destination is probably not important for this one, but then and then the pulse, the signal it received, and it's going to do some work and produce all of the outputs uh, for its destinations, right? So the ones that it's supposed to go to. So once I've done that, then you can think about is I can kind of just iterate through this list as I can use the list, I should say, to quickly find like the communications that I want to process. Um, so let's talk first. What I actually want to talk about is how we parse this configuration. In this case, I didn't act because that's the entirety of the input, right? Is this whole input right here, all of this is actually just your configuration, right? And it's a map of string, right, of module names to their like implementation. So how do you parse it? In this case, I didn't use nom. I thought I mean, this seemed easy enough to do. So because if you think about what these actually look like, is it's just like a key, a source, and their destinations. And so I just kind of treated it that way when I was parsing it. So I split by the arrow indicator. And then I know the first part is the name or the source, and the last part are the destinations. So how do I parse the name? I use this thing to extract the type and its name. And that's because you can see like the very first character actually describes what it is. And that's here in the instructions. It says, if it's a flip-flop, it's going to be prefixed with this. If it's a conjunction, it's going to be prefixed with this. And then the broadcast module, there's only one of them. And it doesn't have a prefix. So that's kind of the thing I'm doing right here. I'm going to, like, from the first part of splitting this up, I'm going to extract the type and name by just checking what the first character is. So this is a funky way of, right, because we're using UTF-8 for our character types, getting the first byte is not quite the same as getting the first character. I mean, in this case, it's ASCII, so it would work, but this is kind of the idiomatic way of getting the first character. And so we say if it's a B, then we know the type is broadcaster, and we can just include the whole name. If it's got a percent or an ampersand, we know those are special types, and so we want to strip that off of the name. So the output of this parse module is going to give you like a character, which is the type, either B, ampersand, or percent, one of these. And then the actual name, which in case of this is the whole thing. For B, it's the whole name. Otherwise, we're going to strip off these for these two. And then the list of destinations, which is just a separated list of those, right? So that's how we parse the module. Then how do we parse the whole configuration? Well, we obviously want to keep a track of our hash map. We're going to use, this is going to be our our final map in the end. But we want to get all of our modules, so we just call input lines map self parse module. So this is going to take each line and call parse module on it for us, right? So now we're going to have a vec of this right here, a tuple of a character, which is the type, a string, which is the name, and a vec string, which are the destinations. So what do? At first, it may seem, oh, well, I can just call a new thing on that. But for the conjunction, you actually want to know the list of inputs, right? If you remember, the conjunction is keeping track of its inputs. So we actually want to know what the inputs are of each of the modules. So I do a quick thing here to track the inputs. It's not a lot. I just loop through each of the modules, and for each of the destinations, the way to think about it is you kind of do a reverse of this, right? So you have this, and now you're actually going to have a destination with all of its sources. So it's the opposite of the input you're given. That's all I'm parsing right here. And that's because when I'm down here, now I can say, okay, based on the type, if it's a B, I create a new broadcaster, and that's just, broadcast new with the name and the destinations. If it's a flip flop, I do the same name and destination, but I now am creating a flip flop. If it's an ampersand, it's a conjunction, and I do need the name and the destinations, but I also need its inputs, right? Because I want to track its inputs, and so that's what I'm doing right here. And so what does this do? All of these, basically, I create a module, which again is a pointer to something that implements handle communication, which all of these do. I'll show you in a second. And then I do a map insert on, so I insert that into my my like map of all of the modules that I have, right? I do some additional work here. This is to create the mermaid diagram. So this part you see right here, this is a mermaid diagram. I don't know if you guys have used mermaid before, but it's kind of you can think about it as like diagramming as code. I like to use it a lot. And so when I was trying to visualize part 2, I wanted to be able to like look at something like this to see what's going on. And again, we'll talk about part 2 in a second, but in order to do that, I kind of needed, instead of like tracking like a hash map of strings to these communications, I actually wanted a list of all of the modules, so the strings to their destination strings, because that's what this would print out right here, right? So this is not actually useful to the algorithm. It was just for implementing this mermaid function, which is right here. I won't talk about it much, but the idea is you want to be able to like start at the top. Mermaid doesn't do a good job of like knowing what should be at the top and what should be at the bottom. And so the way that you figure that out yourself is we're going to start at the broadcaster, find all of its children, and print them out. And then we're going to find all of their children and print them out, and so on and so forth. And that's what makes it look a little bit cleaner. This is still, I'm sure it's a bit of an eye chart, but that's what this mermaid thing is doing. Is we want to create a graph, but because there's like loops and interconnections, like maybe you can't see very well, but over here in the corner, you can see like this QS can go to SC, which can go to MV, and MV outputs back to QS. So you can get these like cycles right here that can happen for quite a while. Even though MV is sending it to other directions, there's a potential cycle going on here. And so if you were just to try and like print them all out, it wouldn't work, right? So I track the queue, which is like the children that I need to process. I'm basically doing a breadth first search on the tree, but not processing anything that I've already seen. And that's what the mermaid code does. So if you want, you can look at the code and see how I did it, but I won't go into much more detail of that. This is just for display, and that's what this is for. So when I'm doing the parse, I keep that so I can do the mermaid display for it. But again, it's not part of the algorithm. What's part of it is this output, right? Is so a configuration, I want to know once I have it, if something says, hey, output this to here, I want to be able to look that up by this, and then I'll know how to process that, right? So let's just look briefly at what each of the modules look like. I have a state tracker here for my flip-flop device or module, and each module is close to the same but not quite. So the flip-flop, I have a name, I have a state, so is it on or off, and then I have a list of destinations that I'll be sending the messages to. When I create a flip-flop, it defaults to off. That's just from the program. And so then what do I do? Well, based on the paragraph, right? If it's a high pulse, we do nothing. So we can send an empty list of communications. If it's a low pulse, though, then I want to do something different based on the two states, right? Obviously, I want to flip the state. So if it's on, I go to off. And if it's off, I go to on. But if the previous state was on, I then want to send a low pulse to all of my destinations. And that's what this does. You'll actually see something along these lines. I could probably abstracted this into a function, but basically I'm iterating over all the destinations, creating a communication for all of them. In this case, because it's on, I'm sending a low pulse. And I just collect those up in a vector so I can send that to that's the result of my handle communication. Again, so the way this just works is if it's high, we do nothing. If it's low, we want to test if it's on or off. And based on if it's on or off, for each of our destinations, we want to send a low or a high signal. That's what we're doing there. The conjunction, again, this one, we want to track the inputs. So not only do we have the destinations, but we have the inputs. This is the like quote unquote state we're tracking for the conjunction. So when we create a new one, we get a list of its inputs and a list of its outputs, and we're going to create this little map, right? The hash map of its inputs, and they're all going to default to low. So the handle communication here is the first thing we want to do is update our inputs, right? That came from the code. Is the first thing you do is you update the input. So we just insert on our map of inputs the pulse that we received, right? So that will update the state. If it was low, it's now high. If it was high, it's now low. Whatever the pulse was, it's now that state. So then we just need to determine what pulse to send. And again, it said if all of the inputs were last high, then send a low pulse. Well, we can just iterate over all the values and verify that all of them are high, right? So if all of the values are high, then we send a low. Otherwise, we send a high. And then this is, again, essentially like what we were doing before. We're just going to iterate over all the destinations and create a communication for given the pulse to send, right? So this thing that we calculated up here. Again, I don't think these are too complicated. It did take me a little bit of time, though. I read the paragraph. Admittedly, I read it when I was still groggy, but I read the paragraph and I was like, oh, what's going on here? But once you understand what's going on, this code actually isn't too difficult, right? And the handle community or the broadcast one is even simpler, right? You just have a list of destinations, and whatever you get in your communication, you're literally just going to send it back out to all of your destination endpoints, right? So that's like setting it up, right? You think of what I've done here is I've essentially created this whole list right here. I've created, or this whole map right here. This whole eye chart is now in code, right? So the question then is like, how do I process a button push? And that is in this function right here, push, right? So imagine me pushing the button. What does that look like? Well, we already know from the code that we're tracking our lows and highs. So we're just going to keep track of those. And then again, we want to keep track of all the work we have to do, because whenever an output occurs, right, I want to process that output, but I don't want to like process it until I've processed all the previous outputs that have occurred. And again, like I said, the best way to implement that in Rust, at least from my understanding, is a VecDeque, right? I can push new work onto the back, and then I can pull old work, or the oldest work, or the work that I need to do most recently is off the front, right? So you can see I start by pushing the button. This is the push the button item, and it's sending it to the broadcaster, and it's sending it with a low pulse, right? That's what's described here. Like when you start it, you push the button and you send a low pulse to the broadcaster. So that's that initial state, right? And then I'm just going to loop through all of my items on the queue. So as I'm doing this, you've probably seen this before when I was, what would I, oh, like Dijkstra's algorithm is the same thing, right? In Dijkstra's, you kind of had a frontier. In this case, it's the same thing. I'm just going to keep popping work off to do and putting new work on the end of it so I can process it later. With Dijkstra's, I think I was using a min heap, so I was doing like the most important stuff, but the idea is the same. I'm just going to be popping work off and putting new work on, and I'm going to keep doing it until there's no work left to do. So I obviously at this point we want to update our trackers when we have some kind of communication. We want to increment our lows or highs, whatever it is. And then we just want to look up what the module is that we need to process, right? So this communication will have the destination name. So we want to look that up in our map. And if we get it, we now have a module that we can process. If we don't, we know we've reached one of those terminal states, which I've talked about earlier, and we don't need to keep processing this path anymore. So we can just be done. We can continue on to the next work to do. I call this helper function for part 2. We'll talk about that in a minute. But for part 1, the most interesting thing is we then, now that I have the module that excuse me, should receive the communication, I'm going to call that handle communication function for that module. And this is where the trait comes in that allows me to do this. Even though I don't know the actual type, I can call handle communication on it, and it will give me a list of new communications to process. And what do I have to do with them? Well, I just add them to the end of my queue, right? So I take all of those communications and I add them onto the end of my queue, and then I go back to processing. And I'm just going to keep doing that, right? So I do all of that work, incrementing my highs and lows, and eventually you run out of work to do. You hit all of your terminal states hit, and now there's no new communications that are done. And then you can just return your highs and lows, right? That's what this is right here. So we are done with all the signal handling. Return our highs and lows. Okay, so given that, how do you use this in part 1? Well, they say you push the button 1,000 times and then you return the multiplication of the lows and highs, right? The product of the lows and highs. So this is just like a fancy functional Rust way of doing that, right? For 1,000 times, I'm going to call configuration.push. This is some magic for part 2. Remember, one of the things you pass is like a little tracker function. But so you can ignore that for now. But the idea is I'm just gonna push the button 1,000 times, and then I'm gonna update my list, right? And that's a fold, right? This is going to produce a list of highs and lows, and I want to like fold them together, sum them all up, and you use the fold function to do that, right? So I'm gonna start at 0, 0, and then I'm just gonna add my lows and add my highs, and this will fold up. So now I'll have a sum of all the lows and a sum of all the highs for all of the button pushes, and part 1 is this right here. So if I run it, you get some, well, there's a lot of printing for part 2, but if you run it, you get some large number like this, right? That's the number you get. And with that, that's part 1. There wasn't much to it other than implementation, right? We've seen this before where you're kind of given a problem and you kind of got to build it out. And then once you build it out, you just like you do the processing that it wants you to do, and you track whatever it wants you to track, and then you produce it. So the complexity, I think, in part 1 was kind of figuring out how to represent these. Because Rust is a statically typed language, we have, at least in my mind, you want to try and do things like, oh, I'm going to have a handle communication trait that's kind of going to help me, deal with this stuff, right? If you were doing it in Python, you could potentially just have them all be in the map and just call the handle function. It would kind of figure it all out for you. You could potentially do this without a trait from an analysis point of view. You like, for example, you could say maybe all of the functions are the same, and I just have like a handler for each of the types, and so I know how to do each of the types. That it's a little hard again because the conjunction is interested in the inputs. The flip flop is interested in tracking its own state. So how you would track those in different ways, I don't know. I would be interested if one of you had another way of doing this. That would be cool to see. For me, it lent myself to at least having a trait where I can handle the communications for each of the modules, and I don't need to understand the implementation details. I think I talked about that before with like Dijkstra, is like when sometimes your logic, the way that you're doing something, maybe you don't actually care about like the underlying thing of like, how do I find a neighbor, or how do I know if I'm at my goal state? uh, as long as you have some function that will do that for you, then you can like process it, right? Imagine what I like about this is the simplicity is if part two was, oh, there's actually two additional types, now do the processing. um it would be really easy to just create those new types and then add them to your like creation stuff, set it up. But then this logic doesn't change at all, right? Not this one. This push logic doesn't change at all, right? So anyway, that's why I implemented it this way. I think obviously if you're like speed running the leaderboard, implementing it this way is probably not the fastest way to do it. But at least the way that my mind reasons, like this felt like the easiest way to do it in a way that I would like understand and be able to like reiterate what I'm doing here. Okay, so part two. What happens in part two? You've done all this work, and it says it's pretty short. We can actually almost read it. The final machine responsible for moving the sand down to Island, right? So you've got all these machines now working, and it says the final machine that you're worried about is named RX. And the machine turns on when a single low pulse is sent to RX. So now you can think, yeah, I'm going to go through this flow, this whole flow, and I'm going to track. I'm interested when RX hits low, right? That's essentially what it's saying. It says reset all the modules to their default states, and then waiting for all pulses to fully be handled after each button press. What is the fewest number of button presses required to deliver a single low pulse to the module named RX, right? So it's asking you, hey, if you run this and you push the button, how many times do you have to push the button until RX way down here at the bottom in this little eye chart gets a low signal, right? That's what it's asking, because that's what's going to turn it down and get it processing. Well, you can see the puzzle solution, at least for me, was extremely large. It's some other big number. I didn't discover this initially. What I actually did was I called the run function in a loop and waiting until I saw an RX hit true or hit low, receive a low signal, I guess I should say. And it just wasn't happening after like 20-30 seconds or something like that. I'm like, oh no. It's one of those things where it's never going to finish. It's going to be some huge unbearable number, right? And so that's when I said to myself, okay, I need to do some analysis on the input and see if I can figure out what's going on. And that's where the mermaid chart came in. I said to myself, okay, let me try and chart this. I think in previous days I did it visually by hand, but there were a lot of them, right? Like in this one, when I looked at all the stuff, I was like, there's quite a few of them. I don't know that I'll be able to do it. And that's what led me to use Mermaid, is because I could programmatically print out. If you look at the way the mermaid diagram is you just give it the, hey, this item points to this item, and then this item points to this item, so on and so forth, and then it will build that for you. I said, okay, let me just print out the mermaid diagram and see what it looks like. And this is what it looks like. And so you could clearly see there's a top broadcaster, and you can clearly see there's a bottom RX. And so what I started looking at, well, what comes from RX? And it turns out the only thing that inputs to RX or outputs to RX is KJ. And that's what I think I describe right here, right? RX is attached to KJ, which is a conjunction. And if you remember, the conjunction will only spit out a low pulse if all of the pulses that it last received from its inputs are high. And so I looked at there's LN, VN, ZX, and DR for my input. So clearly there's 4 of them that are coming into this KJ. And so the only time KJ, maybe I'll try and zoom in a little bit here. I am pressing zoom, I promise, but it's actually not helping. That's hilarious. The way that you know that these 4 are the only time KJ is going to send a low is if these 4 have sent a high, have last sent a high, I guess is the way to think about it. Okay, so what should that make you think about when you're analyzing this? We saw something like this in day 8, right? It was a cycle analysis problem, and that was that's what immediately my mind brought to is like, oh, clearly there's only 4 inputs to KJ, and so there must be some point during all of the processing where this one has sent a high, this one sends a high, this one sends a high, and this one sends a high. So you can say there's some cycle going on, that there's got to be some cycle going on where these 4 eventually all produce high at the same time. So I'm actually what I want to track now is these signals right here. And that's what I did in my thing is I said, okay, I'm going to start tracking these. And that's where that helper function comes in. So if we go back and look at the what was it called? Push function. I have this little helper function. The algorithm doesn't care, but it just passes the communication to the helper function. And so in my part 2 analysis, I'm going to go through it, and I had to run this a few times. I started at 1,000, that didn't do anything. 20,000 seemed to give me the number. I did 1,000,000, but it was taking a while. And so I'm like, okay, let's go to 20,000, see if that helps. And it did. I'll show you what it looks like. But I have this little helper function that when I call my push button, I pass that to it, and it's going to perform this. It's going to run this code right here, this closure. And what does it do? It just checks to see if LN, VN, these values right here are in my source. And if that source is high, right, that's an indicator that I've sent a high signal to KJ, right? And if it is, I want to track that in my tracker. So I've built this tracker that is gonna let me know all of the times in the 20,000 iterations that any of these sent a high signal to KJ. And the reason this is helpful if you think about it, if you can find some cycle in all 4 of them, you can then that when all 4 of those match, that will be the point in time when KJ will trigger on and RX will receive the low signal, which will be this answer to your problem, right? And that happens to be a least common multiple problem, which I think I pulled it from day 8. I didn't remember how to calculate least common multiple, so I just copied my code from day 8. But the idea is if I can find a cycle in these 4, I can then calculate the least common multiple of those 4 cycle lengths, and eventually that will tell me when KJ all of its inputs will be high, and it will trigger RX to send a low signal to RX and find the answer. So what does that look like? Again, I tracked all the times that I saw a high pulse from these, because I knew the only time it would send a high pulse to these is to the KJ. And then I just printed them out so I could see, right? And so all these are little printouts that are kind of helping me get there. So I'm going to run it and just show you what it looks like. Right, so you can see here's that first tracker. After I've done all the running, I'm looking at these numbers. And at first when I was looking, you can see at DR, you're like, oh, is that looks like maybe it's like some number around 3,000. It was this ln one where it was obvious, right? Clearly this is happening every 4,003 cycles. I'm like, oh yeah, clearly there is a cycle. So I then do the diffs of these, right? So what is the diff between this value and this value and this value and this value? And then you can see here, right? So the diffs for dr are this, the diffs for zx are this, the diffs for ln are this, and the diffs for vn are this. So you can see there's clearly this cycle, right? All of these are going through this processing, doing all of their processing, but these ones are only sending a high signal every 3,863, 3,989, 4,003, and 3,943 times, right? So these are the four numbers. I know that each of the between the four of those, these are the four times, or these are the four like cycle lengths. So now I just need to figure out when all of these like cycles would catch up to each other and all hit on the same time, right? That's the way to think about it. And that's what least common multiple is. So once I've figured out what these four numbers are, I can just calculate the least common multiple of those four and return that solution. And that was it for part two. That was the solution. Again, this was a problem where you had to like, part one was kind of an implementation, and part two was, oh, there's got to be a gotcha to this. I need to look at the output. And so I would really encourage you to learn some diagramming thing. I know there's programming languages that have them. Like I looked around for one for Rust for a minute. I think there was one called Term Tree, but it didn't really look exactly how I wanted it to. And I had the, oh, hey, I use Mermaid all the time at work. Why don't I just use Mermaid for this? Notably because it has this simple structure right here that I could easily output from my source input test, my input file. So I visualize it, and then that allowed me to see, oh, KJ clearly only comes from these four, and because it's a conjunction, RX is only going to turn on when all four of these are on. That should be a signal, at least in my mind, it was to me, oh, that's a signal that there's got to be some cycle going on here, right? If I can't solve it in the first, 30 seconds of checking, maybe there's some cycle going on. So I should say this is not a generalized solution. If you look at this code and you run it, it's only going to, well, part one should work for any input, but part two is only going to work for my input, right? I don't know what your cycles look like. I imagine they will look something like this though, right? Maybe this middle section doesn't quite look like that, but I imagine you'll find some section down here that says, oh, there's a conjunction, and the conjunction only sends the correct signal when some number of these are processed. I don't know if there's a generalized solution for that, because I don't know how the cycles are produced. Maybe yours only have 3, maybe yours only have 5. It's just going to be different for each input. So the question is like, sometimes I get asked this, well, is this kind of cheating because it's not a generalized solution? I don't think so. Remember, these are puzzles, and they are programming puzzles. But and so obviously you want to solve the puzzle, but your goal is to like solve the input problem, right? So, and this is now the second day where cycle analysis was the solution to it. And so those puzzles tend to lead themselves to like non-generalized solutions. Alternatively, I maybe I just don't understand enough about like the cycle problems to be able to like come up with a generalized solution. But I imagine most people, I'll have to look at the day. Maybe there is some general, and if there is, I'll talk about it later. But I think most people kind of looked for cycles, and that's how they found it. Because I don't know how. Again, the answer was some absurd number, right? Hundreds, thousands, millions, billions, trillions, 240. So mine had to go 243 trillion times. That would have taken, days to process, I presume. So or at the very least hours, right? I don't know how many million I could do per second. I can't do it in parallel because each one alters the state, and so you couldn't do it in parallel to try and speed it up. You'd have to do it in some sort of like linear fashion. So optimizing the thing would maybe be helpful and important. Again, though, I just feel like this happens from time to time where maybe it's not teaching you like a technique like Dijkstra, which is what we talked about before, or KD trees, which I didn't know about, but apparently is what kind of where I went with the previous day. Some of them are meant to teach you, just to solve a problem, and you do need to learn stuff, right? Like I felt like this one, the input at least lent itself to using a trait, and so in that sense, um, making sure you understand the ways like an interface system works in whatever language you're using would be helpful here. So there you go. That was my thoughts on day 20. I thought it was a great problem. The first part of it was obviously just can you implement this tree in code? And so thinking about that and reasoning about it probably takes a little bit of time, but relatively easy. The second one was clearly I can't solve this. Can I find some simpler solution? Um, I can't solve it via brute force, right? Just go iterating until I hit it. So can I find some simpler solution? And it turned out to be cycles, right? This is if you enjoy Advent of Code and want to keep doing it, but maybe you get stuck on certain days. Cycle detection is always I guess I can't say it's been every year, but I can think back of like obviously we had one on day 8 where I got the previous code from, but there's been previous years for sure where there's some kind of cycle detection going on. So just keep that in mind that sometimes what you ought to do is when the problem seems large, graph it out some way so you can try and visualize it, and that will help you get there. You might have been able to get there without a graph, right? So if you knew you were at Rx and you looked at your input and say, oh, Rx comes only from KJ, and how do you get from KJ? Oh, it's these four right here. You probably figure that out if you're just reading through it. But at least for me, it always helps to visualize this. I don't, if you were like speed running going for the leaderboard, you probably don't have time to do something like this, but I am not fast. I just like to solve the problems, and I like to think about them and make sure like the solution I'm implementing like is clear and concise. And so for this day, visualizing it and cycle detection was super helpful. So there you go. Again, thank you everyone for watching. I hope you all have an amazing day, and we will talk to you tomorrow for day 21.